All right, so we will continue this discussion on columns. Now we are getting into this part three of the module. Here we are going to discuss about the behavior and analysis of short columns under axial compression and bending. So in the last part of the video, we discussed about how the columns are behaving under pure axial compression, right? So now we will see when the columns are subjected to both bending and axial compression, how is it going to behave? And the expected learning outcomes, the student should be able to understand and discuss the effect of load eccentricity in the column behavior. Okay, at when the axial compression is applied at different eccentricities, how is it going to behave? And explain the salient points in the axial compression bending interaction curve. We'll talk about what is that, and then discuss the IS code provisions listed in to derive the PM interaction curves. And we also understand the procedure, and we'll solve one example how to derive axial compression bending interaction curve for RC sections. All right. So pure compression, we know that the entire cross section is subjected to same level of compressive strain. And as per the IS 456, we have seen that the failure strain should be considered as 0.002 for pure axial compression. So if you look at it, when the column is subjected to pure axial compression, like the one that we have seen here in this, now the eccentricity here is 0. So that means the load is exactly at the applied at the CG of the cross section, and you have entire cross section that is subjected to same level of axial compression. So this value we take it to be 0.002 as per IS code. Now you can have the other extreme when the column is subjected to pure bending moment. Okay, and here the eccentricity of this applied axial compression will be at a very large distance. Theoretically, it will at an eccentricity of infinity. Then only you have the column that will feel only the effect of bending, and that would be basically pure moment. And you should also know here in this case the neutral axis depth is going to be infinity, right? Because it's under pure compression, so you will not have any bending. So when you have no bending, your neutral axis depth will be at infinity. Here xu will be actually minimum. Okay, so there are two extreme cases. For pure bending, eccentricity will be infinity. For pure compression, neutral axis will be infinity. And for pure bending, the neutral axis will be at the lowest value. So this you have to keep in mind. Now we can also have column that is subjected to a large moment and relative to the axial compression. So that means the eccentricity will be substantial. So you will have high bending moment, and as you know, the bending moment is P times E, right? So the mu will become high, and it is also having axial compression. So when you have bending moment high, so you will have section neutral axis will be most of the time it will be neutral axis value less than your depth of your section. Okay, when you have a large bending moment. You can also have another situation where eccentricity is very low, and the column will be subjected to large axial load, but the bending moment will be small because the eccentricity is small, right? In this case, you will have the entire cross section will be under compression. However, the compression at uh, the one side will be larger than the other, but the entire section will be in compression. So you can see that you have different scenarios. In this case, you will find that the neutral axis depth, when I put it here, so the neutral axis depth is going to be much larger than your depth of your section. Okay, so here neutral axis will be less than depth, and this will be the minimum. Or for pure axial compression, neutral axis depth will be at infinity. Now let us see. So the strain distribution over the column cross section, it depends upon the loading condition as we have seen in the previous case. You have pure compression, you have pure bending, then you have different combinations of bending and compression that is possible. Okay, so each axial load moment combination has a different strain distribution, or in other words, for any strain distribution over a column cross section, I can find what are the moment and axial loads at failure that is creating that strain distribution. So, or in other words, if I assume different values of neutral axis depth, I can find out what is the PU and MU that is causing that particular strain distribution. Okay. So if I know the top compressive fiber strain and the depth of the neutral axis, I can find out what PU and MU that is causing that. Okay. So that can be established. Now, you can have the strain distribution can be such that the tensile strain can exist, as we have seen. If the neutral axis within the cross section, you will have 10 bars on the tension side will be under tension. Okay, they may be whether yielding at tension at failure or not, or you may also have a condition that the tension reinforcement may not have yielded also. Okay, and you can also have a condition that the tension steel can yield just when the concrete is crushing, as we have seen in bending case. That is a balanced failure. Okay, and of course the concrete on the tension side for this analysis, we are going to assume that it is going to be cracked. Okay, now let us see pictorially. As a design engineer, I want to establish for a particular cross section what is the maximum uh, uh, capacity that column section can take under different combinations of axial compression bending. So that is what we usually plot, which is we call that as axial compression bending interaction. We write axial loads in the y-axis and the bending moment in the x-axis, and we know bending moment is pu times e. So this is the shape. This is a design interaction curve, we call it, and this is also sometimes called as failure curve. Okay, I mean the failure definition is defined when you are, as we have seen, the failure is always denoted in concrete when the top compressive fiber reaches a particular strength. In bending, we have taken 0.0035. For pure compression, we have seen that we should take 0.002. But when you have a combinations of bending, compression, bending, epsilon Cu will be between 0.002 and 0.0035. Okay, so we will see in what cases that we have. So this is the first point, pure axial compression, and we have seen that the entire cross section will be subjected to same level of axial compression. But this is a theoretical thing. But the code is saying that no, you have to take some minimum eccentricity also in consideration. So if you plot this curve with E is equal to E minimum, so E minimum, as you have seen, we have seen at least to 20 mm should be considered, or it should be L by 500 plus D by 30. So that is your E minimum that we have to take. So when you do that, you will find that the capacity, the axial compression capacity is Pu naught, which is slightly less than or lesser than your pure axial compression capacity. So in this case, E is equal to 0. When I'm moving along the y-axis, so there is no bending. So it is only pure compression. So E is going to be 0. Similarly, I can have a load, or in other words, let's say if I take this column, right? So we have seen this in the column behavior, and I apply this load, and this is the eccentricity. Okay, so you see here, if I start increasing this P from 0 to some high values, when P is 0, the moment is also 0. So when P is certain value, I get moment also some value. So what this curve actually indicates is a load moment curve. Okay, so this load moment curve, if you see here, it is going to be following a slope of 1 by E. Okay, so the slope of this curve is going to be 1 by E, or in other words, we are taking P by M, which is nothing but 1 by E, right? So for this condition, you will find that you will, and then we can also, when E becomes E naught, I can create a strain condition such a way that the bottommost fiber is going to have zero compression, or you can say that neutral axis depth is going to be equal to the depth of the section. Now you can also create a condition, or I can increase the value of V to balanced eccentricity such a way that the bottom level of your section is going to have yield strain, the top is going to have reaching its compressive failure strain simultaneously. So that, like what we have seen in your flexural case, this is your balance condition. So depending upon what value of E that you have, when E is 0, pure compression, and V is equal to E naught, you are reaching a situation that neutral axis depth is exactly equal to the depth of the section. Then when E is equal to EB, which is the balanced condition, you create a balanced failure, that means top compressive fiber is reaching epsilon cu, and the tensionmost bar and the bottommost layer of the steel is going to reach its yield value. So that is a balanced condition. Now you can also have, so whenever the load eccentricity E, when it is less than EB, we can see that this is called as compression failure. And in bending, we have seen that concrete is not allowed to reach its failure strength before the steel is yielding. Code wants the design engineers to design only under reinforced sections, right? But here we are dealing with a compression member. So predominant role of column is to resist the compression loads. In addition to that, you will have shear and bending also. So we cannot make the column to fail always in under reinforced mode. So the code is allowing the members to fail in compression mode. So when E becomes less than EB, then you have the column behavior will be dominated by compression failure. Okay. So when E becomes larger, when it is becoming more than your balanced eccentricity, then you have tension failure. That means before concrete at top reaches its compressive failure strain of 0.0035, your bottom rebar is going to yield. So, and we know that in pure bending and column have same, usually column will have symmetrical reinforcement, and you will have same reinforcement at the top and bottom, or the reinforcement will be equally distributed on all four sides. So columns under pure bending will always behave like an under reinforced section. So that is the reason in pure bending you will have tension failure. Okay, so this is the way we can classify how the particular cross section is going to behave under different combinations of axial compression and bending. And this green color curve, what we have drawn here, right? So this is called as failure interaction curve. So at any point, if you look at it, this is the combinations of P and M this particular curve can take. Okay, I can have a high axial compression, low bending, or I can have a high bending and low axial compression. So that depending upon the design requirement, we have to calculate the capacity of the section and find out whether to increase the concrete strength or put more steel. That we need to look at it. Again, we have seen that if you want more axial compression for a particular cross section, you should either increase the size of the column or you should increase your concrete strength. If you want more bending strength, then you know that you need to put more tension steel. So we have seen that. Now let's see. So when the loading eccentricity is less than corresponding to the balanced failure condition, the yielding of longitudinal steel in tension will not take place, and the failure occurs at ultimate limit state by crushing of concrete at highly compressed states. So that is a compression control mode. And in this case, the compression reinforcement may or may not yield depending upon the grade of steel and its proximity to the compressed states. Again, we define the failure as under reinforced not depending upon what happens to compression steel, but what happens to tension steel. Because columns are compression members, you can have compression dominant failure mode. Now let's see tension failure. So if the loading eccentricity is greater than that of balanced failure condition, when E is greater than EB, the failure will be initiated by yielding of tension steel. Okay. Again, the outermost longitudinal bars in tension side of the neutral axis first will undergo yielding, followed by successive inner rows, and then tension side of the neutral axis with increasing strength. So you will have a progressive yield when you have multiple layers of steel, right? So then finally, the final collapse will occur when the concrete at compressed edge, highly compressed edge, will get crushed. Okay. So anyway, final failure will always happen when epsilon cu reaches its final value. Okay. Again, epsilon cu is not going to be constant. Okay. Here, when we deal with columns, epsilon cu can be between 0.0021 and 0.0035. This is one thing that you should always keep in mind. Now let us see. How to find the strength of these columns. Okay, so this is what we have said. When E can be between 0 and infinity, and the strain profile is non-uniform and it can linearly varying across the cross section, and you can see the epsilon cu is going to vary between 0.002 and 0.035. So when neutral axis depth is within the cross section, it is 0.0035. When neutral axis depth is going more than the depth of the cross section, then you will have epsilon c varying between 0.002 and 0.0035. Right. So you can see in case of eccentric compression, the depth of the neutral axis with reference to highly compressed states can vary from minimum value to infinity. Infinity will happen when you have pure compression. So there is no neutral axis, right? So eccentricity is zero. And when the loading eccentricity is very low, then the entire section can be subjected to compression and neutral axis can lie outside the section, or XU can become more than depth of the section. And in that case, you will have epsilon U between it is going to lie between 0.002 and 0.0035. So let us see how that we calculate. Okay. So let's see this case. And you see here, in this case, I have eccentricity which is less than the depth of your balance condition where you have compression dominant behavior when XU has become more than the depth of the section. So you see here, these are the strain condition. Now let's look at two cases. This is your pure compression case, okay, and this is your pure compression case, okay. This is one. Let me draw it with another color. When you have XU equal to D, okay, so then you get this, okay. So you see here this, so this is your pure compression. This is you, this will happen when XU is equal to D, okay, and this will happen. So this is basically for pure compression, okay. So what the code is saying that when for pure compression you have 0.002 for the entire cross section. When XU is equal to D, then you have maximum strain of this value, which is 0.0035. So if you, in these two extreme cases, you know that at what depth this strain will reach from 0.0035 to 0.002. So we know that when XU is equal to D, at a distance of 3D by 7, it is going to reach a strain of 0.002 for this when X is equal to D. When X is equal to D, at a distance of 3D by 7, the strain at this location is going to be 0.002. So what the code is saying that when XU becomes more than the depth of the section, always you are going to have uh, the top, the strain condition that what I'm using. For example, let's say when X, in this case, for example, here you have XU. In this case, let's say this is your XU. Okay. In this case, XU has become greater than your depth of section. So what the code is saying this, in this case, the strain has to pass through this fulcrum point of 3D by 7. Okay. So at or that this value, it should be equal to 0.002. Okay. So I don't know, this is the epsilon cu that we are trying to find out, okay, corresponding to this, okay, from here to here. So this is your epsilon cu. So again, two extreme for pure compression 0.002, when x is equal to d 0.0035, but for any other values of xu which is greater than the depth of the section, what we are saying is you will have epsilon cu, but that epsilon cu has to pass through this point, fulcrum point of 3D by 7. So from the top compressive edge. So that at that strain, at that location, it should reach a value of 0.002. So that's what the code is mandating. Okay. So if you go with this approach, if I'm taking only this, let's say this similar triangle, okay. So I'm taking only this similar triangle. Okay. Let's say this. So this distance, what is this distance? This is going to be, if this is 3D by 7, so this distance is going to be XU minus 3D by 7. So because the entire depth is your XU. So this difference is XU minus 3D by 7. So now what is this? This, if I take this as your epsilon Cu, then this distance is going to be, what is that? Epsilon Cu minus 0.002, only this, right? And what is this strain? So we can see here, and this is also going to be 0.002 strain. So if you substitute that, through similar triangle, you will find that epsilon cu by this similar triangle, this distance 3d by 7, this distance xu minus 3d by 7. So this I can find the expression for this value, which is epsilon cu by 0.002. You can write that epsilon cu minus 0.002 by 3d by 7 should be equal to, right? So 0.002 divided by xu minus 3d by 7. So if you simplify this, then you will find the expression for your epsilon cu as 0.002 plus times 1 plus 3d by 7 divided by xu minus 3d by 7 when for neutral axis depth more than depth. When neutral axis depth is less than d, then you know that your epsilon cu is what is the value? Your epsilon cu will be 0.0035 only because it's a bending dominant behavior. So epsilon cu you can keep it as 0.0035. So I need to change my epsilon cu only when your xu becomes more than the depth of the section. So using this similar triangle, I can find this expression like what we have discussed. Right? Now let us look at the two scenarios. How to calculate what is axial compression and bending moment for two different scenarios. Let's look at the traditional case. We have also done the moment curvature behavior for a section that is subjected to axial compression. It is similar to that. So I'm taking a cross section, column cross section like this with B and D, and it is having a effective cover depth in compression side of D prime, and the CG of the section is written here as CG. And what I am taking is each you have now, you see you have multiple layers of steel. Okay, I need to calculate all the contributions of the steel depending upon whether they are in compression or tension. So I am going to take that as the distance of each layer as yi, and yi when it is above the CG axis I am going to take that as positive. When it is below the axis CG axis I am going to take that as negative. Okay, so this is for sign convention. Now, depending upon what is the strain that I am assuming, so in this case, if you see neutral axis is lying within the section. So this is your neutral axis depth, right? So what would be epsilon cu? Epsilon cu should be taken as 0.0035. When neutral axis is falling within the cross section, epsilon cu will not change. It is 0.0035. So then you will have these bars will be in compression. Okay, and these bars will be in tension, right? So below the neutral axis will be in tension, above the neutral axis will be in compression. I need to calculate what are the strains in the steel. Anyway, we are assuming a linear strain profile. So if I know epsilon cu and if I take xu, then I can find out the strain distribution in all the locations, right? And we know what is fc. Okay, for a rectangular section like what we have seen here, what is fc? Fc is equal to 0.36 fck times b times h, right? And now what is the stress in each layer? So this is in compression, these layers are also in compression. So again, what is the layer, what is the force contribution from all the steel layer? You will find that it is going to be area of the steel in that particular layer multiplied by stress in that particular layer. Now the green colors are all in compression because they are above the neutral axis. Now the red color curves are in tension, that is why the direction is also changed. Okay, right? So this is the strain distribution. Now this is the you can have stress distribution from strain. You can get your stress from your stress strain curve. And again here we are using design curves, design stress strain curves specified by IS code. Okay. In the first part, we have looked at moment curvature using parabolic sustain curve and elastic perfectly plastic curves. Now we will, because we are developing design calculation using IS code. So we are going to use the design curves that are specified by the IS code, right? And that is the reason the concrete force is written as 0.36 FCK BH, right? So if you go back, now let's look at what are the invoke the axial force equilibrium, right? Now this is not pure bending. When you have pure bending, If I sum all the forces, it should go to 0, right? Compression should be equal to tension force. In this case, it will not be 0. Fc and Fs, when I sum them up, you get some net axial compression. Sometimes you can have axial tension also, right? So the summation of all the forces, what you do, you will end up with some positive value that indicates that that is the compression force that is acting in this section, that is creating this kind of a strain profile. Okay. Similarly, the moment resistance also we can take. So now how do we take the moment resistance? So you know this Fc is this. So you know this distance, which is basically, now here in columns, it's always we need to find uh, moment resistance about the centroidal axis. Okay. So you need to find the moment resistance always about centroidal axis. Now why is it we should do that? The reason is when we do structural analysis, we always find the stress resultant, that is your bending moment and your axial force, everything, only with respect to the centroidal axis. So that is the reason even the capacities I need to evaluate it with respect to centroidal axis. Okay, so if you do that, so it is going to be Fc multiplied by this will be your lever arm. Okay, similarly you have to invoke your sign, so whether it is counterclockwise or clockwise, right? So you have this. Similarly, these layers of steel also will come. For example, if you look at this layer of steel exactly at CG, right? So that moment contribution of those layers of steel will not come because now I am taking moment about centroidal axis, right? So it will not come into picture. But you will have only contribution from this force, and this is your y. This can be y1, for example, this can be y2. So all of them I need to add. For example, in this case, Fc is creating a counterclockwise moment, Fs is creating a counterclockwise moment, Fs2 is also creating counterclockwise moment. But this, okay, now what we are doing is yi, if I go here, it will become negative. So you have to appropriately consider your signs in your calculation. So this is how we are doing. So you can say Fc can be written as AFCKPD, right? So and we will, this is a force in compression. So the A can be written as a function of your Xc. So moment resistance for concrete is again Fc times d by 2 minus h bar. So why? Because we are taking, this is your lever. Okay. Now because we are taking moment about centroidal axis. So this is your d by 2. Now what is this distance from here to here? D by 2 minus your x bar, which is your Fc where it is acting. And we know it is 0.4 to x when your neutral axis is within the cross section. Similarly, I can write out the force contributions for all the steel layers. And now that I've invoked compression as positive, tension as negative, I can add all of them. And similarly, moment resistance, again, we can look at the stress in the steel minus the stress in the concrete of that layer divided by, multiplied by the area of the steel of that particular layer and the distance. So force multiplied by the distance will get moment resistance. So you can take compression as positive and tension is negative. So similarly, the y also will become positive or negative depending upon which layer that you talk about. But moment when you do that, all of them will add up. Okay, so in this way we can talk about. Now we'll go to the more generic case when the neutral axis is lying outside the section. So you see here. Now in this case, my neutral axis has become more than the depth of the section. So this is your neutral axis. Xu is greater than D. This is the condition that we are talking. Now, what is this epsilon Cu? Epsilon Cu we have derived in the previous expression as 0.0035 minus 0.75 times epsilon C minimum. What is epsilon C minimum? Epsilon C minimum is the, what is the strain in the least compressed edge. Okay, so this location, whatever the strain that is there, that is your epsilon C minimum. Okay, so you can find that once your XU is fixed, and you can find out this strain distribution. So that we have found that using similar triangle as we have discussed in the previous part of the model. Now we see here, this is the, if the neutral axis within the section, we know how to calculate that 0.36 FCKBXU. But now only this truncated stress block is actually contributing in compression, right? So there is a part of the stress block which is outside the section that is not going to help in load resistance. So for FC, I need to integrate only this shaded area. So this is the problem. Okay. For a parabolic model that what we have discussed in moment curvature analysis, we converted them into an equivalent rectangular stress block. So we can quickly calculate because everything is converted into equivalent rectangular block. But in this case, for IS code, you have parabolic portion and then a straight portion. So deriving that alpha and beta is more involved. Okay, so this aspect you have to keep in consideration. So if you see now FC, the force in concrete is going to be again AFC times B into D. So the area will remain B into D. Even though the neutral axis is going outside the section, the area will always remain BD in your compression force. Now the A value will change. That we will talk about that. Similarly, moment resistance of concrete is force in concrete multiplied by D by 2 minus X bar. Again, why this D by 2? We are taking a moment about centroidal axis. So similarly, what is the force contribution from each layer? If you have n number of layers, you can mark them. And again, as you said, yi will be positive above the CG, yi will be negative below the CG. So you have to take positive value and negative value. Again, compression is taken as positive, tension is taken as negative. So appropriately, sign convention has to be done. Similarly, moment resistance of all the steel layers can be taken like this, and you have to sum them up. Okay. Now the only challenge what we have here is in integrating this truncated stress block parameter. So let us see how do we do that. Like what we did, we need to find out expression for this A and X bar where the FC is acting. For the cases when XU is less than D, it is pretty straightforward. The code is already giving you the value. But the major challenge is when XU becomes more than D, how do we do it? Okay, because you have a truncated area, right? So this is what we have, case A. So when XU is less than the depth of the section, FC will become 0.36 FCK XU, and this X bar is basically 0.42 XU. So it's very straightforward. So how do we do that? Again, if I write this generic expression for stress as FC, and if I take small elemental width as dy, and if I do the integration, that should be equal to A into FCK BXU. And the stress strain relationship, we know that for stress in the concrete is when strain is less than 0.02, it is following this parabolic relationship. But when strain becomes more than 0.02, the stress is going to remain constant at 0.447 FCK. So we know that, right? So this is a design stress strain curve. So this is the stress strain curve which is specified by the curve, right? So up to this it's parabolic, after that it is constant, right? Similarly, we can find out what is the location of X bar from your first principles. So using this, so if you do the integration, you get A value as 0.36 XU by D when XU is less than the depth of the section, and A value is given as 0.447 times 1 minus 4G by 21 when XU is more than D, and G is given as, so when I do all the integration and I simplify that, I get value for A as this. When XU becomes more than depth, A becomes 0.447 times 1 minus 4G by 21, where G is given as 16 by 7 times XU by D minus 3 whole square. Similarly, X bar 0.416 XU, we know this is the location of your compression for depth. And then when X, this is the critical condition, when XU becomes more than D, then the expression for X bar is expressed in terms of G like this. Okay. So when you do this integration and equate them and simplify that, you will get this expressions, right? Now, what are the stresses in each layer of concrete? And strain is uh, there. So if you see here strain is less than, otherwise, if it becomes negative, then the stress in concrete is taken as 0. If it is going to be less than 0.002, you take that as positive value if it is taken as from your parabolic model. And if it is going to be more than 0.002, you keep it as a constant value of 0.447 FC. Similarly, how to find the strain in each layer of steel? So again, we can, you can using this simple expression for XU on this, I can find out from, say, let's say this is your XU and this is your D. From here, we can find out that expression for this. Okay. And we have also fixed y is always related with respect to centroidal axis. So I can relate that. I can find the expression for a strain in each layer. Again, you will get a positive value for strain if it is in compression, and if it is going to be in tension, you are going to get negative value.